We have two new families of functions. The logarithmic exponential general functions, exponential general functions, and the logarithmic general. Just change color for this one, logarithmic general logarithmic function. So, how they are defined? Let's start. If we consider R a fraction, okay, and a positive number, then we know that a power R, we can write it a using the exponential and the inverse of the logarithmic function. So I can write it like that: a is equal to exponential, okay, power R. Then we use the properties of the exponential function. So you have a real number, so the exponential will be R ln a, which you can write. So this is, yes, so we have this equality. So we extend this definition to our real number, for our real number, and define like that the function the general exponential function. Okay, so ax is defined as the exponential x ln a. Okay, for it is well defined for any x in R and a positive. Okay, so this is our main definition. Okay. Okay. Great. And from this we can deduce, of course, properties. Just using the properties of the exponential, we can deduce many properties, but it's not important. But just let's have an idea how it works. So we have laws of exponents. They work. You have a x plus y is equal to ax ay, as long as everything is defined. A x minus y is ax over ay, and etc. Ax power y will be axy, etc. Okay. Also, if you have e and b x, it's exactly ax and b times bx. Okay, but we don't have to memorize everything, but it's easy. We know how it works. Now, what about the function? What's its derivative? Let's discuss its derivative. What is the derivative? Okay, so the derivative of the general exponential function base a, we say base a, is, so I can deduce it, I will derive. So usually what I do, I don't memorize the formulas related to the general exponential function. I come back to the exponential function, the basic one we know. I know how to derive it and use the chain rule formula. So each time this is what I do, don't have to. Okay, so to avoid any mistakes, I do that. So I have the chain rule formula that says me I derive the exponential itself. Deriving x ln gives me la. So I have exponential x ln a, which is exactly ln a. It is ln a times the same function. So we have a factor that appears of ln a, and then we can deduce then the monotony, of course, from here. Monotony. So depending on the sign, ax is always positive, but depending on the sign of ln a, we can deduce. Okay, ln a will be positive if a is greater than 1. So ax, so let's say for a greater than 1, the function, the general exponential function is strictly increasing. For a less than 1, positive, okay, x, the function is decreasing. So it's one-to-one function. Because it is one-to-one function, then we can define its inverse. Okay, so here is the inverse of the one-to-one function. Okay, so we define it, yes, because so depending on a greater than 1 or a between 0 and 1, we have then we define the new function by logarithm base a of x equal y is equivalent to say that we have a power y equal x. This is how it is defined. Okay. Okay. Now, okay, what we can, yes, let's now in particular. So let's remark here in particular by base a of x will be for x will be, so how can I deduce it? Yes, so it will be y equivalent to say that ay equal x. So the logarithm base a of x is exactly the ln x we defined previously. Okay, and now if we have, so from this equation, from here we have a logarithm a base ax is x. So if you take both sides the logarithm, then okay, so what we can deduce the following. Then you have ln of a logarithm base ax is ln x, which gives me okay, which gives us a logarithm base a of x, the general logarithmic function base a. Okay, so L times ln a equal ln x. So finally we have the following. Look what we have. We can deduce then the formula for the general logarithmic base a of x. It's nothing that logarithm of x, the usual one, over ln a. So this is my formula, and it is defined for x positive and a positive. Okay, great. Here it is. Okay, so usually I don't then memorize anything. I keep I limit myself to memorizing what is concerned by the exponential function, logarithm function, and the definition and the definitions for the new two functions. That's all. Okay, then everything I can deduce it. So for the shape of the curves, it looks like, since yes, it's a factor of the exponential, so depending on the sign of ln a, so it looks like to the exponential or it has another shape. Okay, for the logarithmic function also a similar remark. So without staying far longer on this properties, let's go and yes, let's work with practice some questions. Okay, let's practice some questions. So the first one, for example, so I can be interested in computing limits, simplifying quantities, depending. Okay, so for example, what if I was asked to compute the following limit of logarithm base 10, the general logarithmic function base 10 x2 minus 5x plus 6 over when x approaches 3 plus. So if I substitute inside, so I see that the polynomial takes the value 0, so the function is not defined, so I have an indeterminate. So I need to know, yes, if it is 0, that means I know the limit. But to see it well, let's come back to the definition of the general logarithmic function. So it's nothing than 1 over ln 10 times ln of so if I factor, or even I keep it like that, it's not a problem. Okay, as x approaches 3 plus, maybe it's better to factor to be sure that everything is well defined here. Okay, I would prefer to do that. So if you factor, you get x minus 3 times x minus 2. Okay, for this. Now for 3 plus 3 and something, this quantity is positive, so it will approach 0 plus. ln at 0 plus is minus infinity. ln 10 is greater than e, which gives us ln 10 greater positive. Okay, so 10 greater than 1, then ln 10 is positive, which gives us everything is minus infinity. Okay, so maybe I will explain here. I have a behavior here of ln of 0 plus, and here I have something 10 greater than 1, then ln 10 is positive, greater than ln 1, which is 0. Okay, so it is positive. So these details are important to understand, to explain why the limit is minus infinity. Okay, so this is one question. I could be asked to, for example, to find the derivative. Okay, the derivative of a function, or integrate, why not? Okay, or derivative, let's say, what is the derivative of y cosine x? Let's go change color and use another color here for each question. So what if my function is y cosine x power x? Yes, say it as power function. Okay, so again here I don't have to memorize anything. Come back to something I know. I know by definition it will be x ln of cosine x. Here the purpose is not to check the domain of definition, so we are asked just to find y prime. What is y prime? So now I look at my problem differently. I need to derive a composite function with exponential and this function. So I will use a general formula. So it will be the exponential to the same second function, okay, times the derivative of the second function. And this one I see it as product and the composite, so I can do it slowly. So still this one is my original function, so I can rewrite it just to save space here. Derivative of x is 1 times ln of cosine x, then plus x, and derive, this is chain rule, I need chain rule, so 1 over cosine x. Now derivative of cosine is minus sine x. Okay, and here it is now. So globally this is my derivative without going through further the calculation. What about integrating? Integration, again, yes, we don't have to memorize particular new integral functions. So let's do just another example here. What about this example? Here I am asked to find an antiderivative of this function. Okay, so go slowly here. Rewrite your function with the ones you know more. So it's ax ln 2 over ax ln 2 plus 1 dx. And now the formula suggests substitution, particular substitution. Let's choose u equal the denominator plus 1, then du will be ln 2, okay, ax ln 2 dx. And now come back and continue your calculation. Okay, once you have this, come back. So we will have ax dx will be du 1 over ln 2 and 1 over u. And now I know my antiderivative. It's 1 over ln 2 ln absolute value of u plus a constant. Then come back to the original variable. So it's ln of ax ln 2 plus 1. That is plus a constant. That is, I have the following antiderivative ln of 2x plus 1 plus a constant. So you see how we can do, yes, all the kind of questions we use it to do. What about the question, the following question? What if you were asked to find the inverse, the inverse of the function fx equal 10 power x over 10 power x plus 1. Okay, so the domain of f here is R, clearly. Okay, but the range, we don't see it clearly. So let's try to solve the equation. So y equal 10x. So the idea of finding the inverse function is expressing x with respect of y. So just do it like that. Y 10x plus y equal 10 power x. Isolate x, so I will have 10 power x times y minus 1 equal minus y. Okay, at this level, y equal 1 is not possible. Okay, so if you substitute y equal 1, this side gives you 0 and the other side you will have 0 equal minus 1. Okay, because we have 0 equal minus 1. So we have to avoid y. So y is cannot, there is no x such that fx equal 1. So y is different from 1, and we will have 10x, 10 power x equal y over 1 minus y. Another, to find the x here, this is something positive strictly. So I need to impose the condition on the y's that have a solution, that this equation has a solution, are necessarily must be positive, which gives me the condition that y belongs to 0, 1. Okay, strictly positive. And finally, now I can find the solution to my equation. So my x here, the only x is so the ln at base 10, okay, logarithm base 10 of y over 1 minus y. So this is my f minus 1 or y with y belonging to 0, 1. So you see, you can have then, yes, all kind of questions. Okay, so these are the new, yes, it adds to, they are added to our library of functions, which allows to model, have more models, modelization. Okay.